Hi, class. Welcome to the next section, chapter 10.2. Today, we're going to talk about the surface area of a revolution. So this is very, very similar to what we were doing before when we were finding volumes of a revolution, except we're not finding the volume enclosed by a curve that's been spun around some sort of axis. Instead, we're going to find the surface area of the solid that's formed by spinning it around an axis. Okay. So let's say that we have an open cylinder. Looks like this, right? So there's nothing on top, nothing on bottom. If we slice this in half, long ways, and unroll it, then the surface area is height of h with a length of 2 pi r, right? Because the circumference of a circle is 2 pi r, so this gives a length of 2 pi r, and h is the other side. Okay. So then obviously the area that would be formed there would be just h times 2 pi r, right? But what if our cylinder is not a cylinder and instead it's shaped oddly? Okay. Something like this, more like a vase or base. Okay. So if we take a slice in order to figure out what the area of a slice is for surface area wise, let's take this and rotate it so that it's centered along the x-axis. This is generally a lot easier for us to understand because then my function is just the distance from the center of the base to whatever height. So I can model this with a function, and it's easier for us to understand. Okay, so if I start to slice this up, if pi minus 1 is the point on the curve that starts one end of the slice, and p sub I is the point on the curve where the end of the slice is the top of the slice. Notice that the radius given in the middle from the center is the height of my function f of x. Okay, so if we want to approximate the length from pi sub 1 to pi, we would do this with an arc length since it's not straight, it's curved, right? If it was straight, it would be a cylinder. So it's not a straight line, it's a curve. So we would use arc length to find the length of between this point and this point, right? The area of revolution, we have r, so remember just 2 pi r, and then our height would be given um, by the length here, okay? So at one side might be longer than the other, right? So we have variable radii or function height. And so the surface area, um, when I rotate this between a start point of A to B, is given by the integral from A to B of 2 pi f of x. So this is 2 pi r, okay? So whatever height is at any x or x sub I, or in this case r sub I, right, is given by f of x. So this is 2 pi r. This is the one of the lengths, and then this arc length is the height, right? So then that would be this function that I have that defines my curve. The derivative, square it, add it to 1, and take the square root. Okay, so this is the surface area when we rotate along the axis of x. If we do it with y, we change this formula, obviously, to represent that change in axis rotation. So let's go ahead and do an example. Okay, so let's find the exact surface area, meaning not a decimal approximation, right? Exact means a symbolic answer created by y equals 1/6 to the x cubed plus 1 over 2x for x existing between 1/2 and 1, right? So this is my interval of integration. This is, and I'm going to rotate over the x-axis. So I need to find the derivative of this, and I need to square the derivative. Okay, again, right? The work that comes into play before I just plug everything in, I have to find the derivative and square it first, and then I can throw everything into my integral, right? So very easy. I have the function given for the height of the function, so I just have to do the surface area part. So when I take the derivative, I get 3 times 1/6, which is 1/2. This goes down to 2. This is 1/2 x to the negative 1. So remember, derivatives go down the power. So this is -2 now, and that negative just gets multiplied in front. So this is my derivative. Okay. Now I want to square this. So if I square this, right, it's a binomial, it's just a perfect square. I square the first term, 1/4 x to the fourth. I square the last term, 1/4 x to the negative 2 times 2, so -4. And for the middle term, I just multiply these together and I double it, right? 1/2 times 1/2 is 1/4 times 2 gives me 1/2. X squared times x to the -2 cancels out and gives me just 1. So there is no x term in the middle here. So I have the -1/2 in the middle. Okay. So now that I have all of my pieces, I can throw it all together into my integral. So remember, it's going to be the integral from 1/2 to 1, 2 pi times my function times the square root of 1 plus my derivative squared. Okay. So 1/2 to 1, 2 pi, my function, and the square root of 1 plus the derivative squared. So what we're going to do from here now is let's go ahead and add 1 into this. So we'll just have 1/4 x to the fourth, a positive 1/2, and then 1/4 x to the -4. Okay. And so now if you look at this and compare it to what we had for the derivative squared, it's almost identical, except instead of a negative, it's a positive. So since we squared this when it was a negative, it's easy to assume that this is the exact same form, but with a positive in the middle, which is nice because if we can factor this to something that's squared and cancel it with a square root, that works very nicely. Okay, so you can go ahead and verify this if you want, but it should be quite apparent that if we were to factor this, this is the perfect square of these two terms. Okay, so we'll go ahead and get rid of the square and the square root sign since they cancel each other out. And from here, now I just have to expand this multiplication of binomials. So I get myself a nice little binomial style um, combination of sum of power functions that I can just go ahead and differentiate, which is much easier to do. So here we will have x cubed times x squared is x to the fifth. The 1/6 and the 1/2 is 1/12. Okay, then I have my 1/6 and my 1/2 gives me another x to the 1/12, and then the 3 and the -2 is just an x. Here I'll get, I have an x on bottom and a squared on top, so that's just x with a 1/4. Then this will be 1/4, and I have a negative and 1 on the bottom. So remember, a negative exponent is like something on, it is an exponent on the denominator. So they combine together and I get 1/4 x to the -1/3 power. Okay. So from here, now you can see that we have a common term. So if I make this a common denominator, this will be 3/12. And so the 3 plus the 1 is 4. And 4/12 is 1/3. Okay, so I have 1/3x. So from here, I really don't have much to do. I could distribute the 2 if I needed to. Obviously, that's not necessary. I can keep it out. I can pull out the biggest common factor of 1/12 to the outside, but that's not necessary either. So we'll just go ahead and start to integrate. Remember, this is going to go up to 6, and I'll multiply this thing by 1/6. This goes up to square, multiplied by 1/2, and this will go up to a -2, and I multiply this times -2 as well. Okay, so here we go, 1/72, 1/6, and 1/8, right? Because it's 1/4 multiplied by 1/2, but negative. And there we go. So I'm going to evaluate this from 1 to 1/2. So we can kind of, the way that this works is we can do it inlaid with each other, but it'll actually be easier just to do one at a time. So the next thing here is 1 to any power is always 1. So the first half is just the exact same thing, 1/72, 1/6, and -1/8. From that, I'll subtract 1/72 times 1/2 to the sixth power. So that's 2 to the sixth in the denominator. Okay, I'm subtracting, so this positive is a negative also. So 1/6 times 1/2 squared is 1/4. And then here, the negative exponent, member is the reciprocal. So this is really 2 squared. So I got 4. The negative and the negative being distributed makes it positive. So from here, I just combine my like terms. I can divide everything by 2 if I wanted to. It doesn't really matter. Just go ahead and find the exact value by adding, subtracting all your fractions, and you get 263 over 256 pi. Okay, and so that is the exact value of the surface area. So this would be obviously units squared. We don't know what the units are. It wasn't given to us as meters, inches, or whatever. So for word problems, just make sure you remember that area is a squared value. So you're not squaring this, but whatever the units are squared, right? So let's do one more example. Let's say we want to find the surface area of x equals square root a squared minus y squared, or y equals 0 to 1/2 a, rotated about the y-axis. Okay, so if you're pretty savvy, if you kind of look at this, this is basically the formula for a circle if we solved for x. Okay, so that's pretty nice little tidbit. If you just kind of can see that, if you squared both sides and then added y to the other side, it would be a circle of radius a. Okay, so we kind of have two choices here, or it's not about the two choices, I'm sorry. So let's go ahead. We have x isolated already, so we're going to differentiate both sides. This will be x prime. Here we use the chain rule. This is a squared minus y squared to the 1/2 power. So that 1/2 comes down, that power reduces by 1. And then we differentiate the inside function with respect to y. So I have my negative 2y. Okay. I need to square this. So if I square this, this just turns into negative 1. And notice before I square this, though, I have a negative 2 and a 1/2 here. So those will cancel out. And I get negative y, a squared minus y squared to the negative 1/2 power. Now I can square it a little bit easier. This will just turn into y squared, and then this term here will just be under a regular, well, nothing actually, right? Just a negative power, negative 1. Okay, so that simplifies rather nicely. And now I can put everything together. The integral from 0 to 1/2 a times 2 pi times my function times the square root of 1 plus this function. Okay, so we did our little pre-work and we just threw everything together. Okay, so from here, if you notice, I have something in the square root times something in the square root. So I can combine these together. So this thing would just multiply across each one of these pieces. So that'll give me a squared minus y squared times here. And notice here, I have the exact same thing, right? So I have a squared minus y squared times its own thing times negative 1. So I have a 1 and a negative 1, so that cancels out to 0. So I'm left over the a squared minus y squared when I multiply it times 1, plus it cancels here and it leaves a y squared. And look what happens. I have negative y squared plus y squared, so that cancels. Leaves me with a squared. The square root gets rid of that, and I have a. All right, so this simplifies very, very, very nicely. They don't always do that, but for this example, it does. So now I'm just going to evaluate this. I'm going to integrate this. So we're going to go ahead and just throw a y here and then evaluate at our bounds. And when I plug in 0, obviously everything goes away. When I plug in y is a over 2. The a's will multiply and square, and this 2 over 2 will cancel out. So I just get pi a squared. Okay, that's a very, very nice value. Okay. That's the end of our video. Much, much shorter than the last video. So I'll see you guys on the next one.